Hello everyone, welcome to this new tutorial on image segmentation with Microscopy image browser. And today I would like to, from one side, introduce you a new 2.5D image segmentation workflow using convolutional neural networks, but from the other side give you an updated overview on how we do image segmentation with using deep learning in MIB. The dataset that I will use for demonstration, as you can see on the screen, it's a U2OS dataset imaged using focused ion beam scanning clear microscopy. The dataset is available for download, and as well as these training sets that we will use sort of today in this video. As an example, you can see some organelles segmented, and we use this 2.5D workflow to segment mitochondria, Golgi, and endoplasmic reticulum from this model. And today we'll start. I'll show you probably the full quick workflow how we can get mitochondria, because it's relatively easy. All the links will be in the description. And I also break this video into chapters, and you can use this timeline to fast forward to any section you want. Okay, what is this 2.5D workflow for image segmentation? There is different ways how 2.5D can be done. For example, one of the approaches is called multi-view fusion. The idea of this approach is that we start with our volume, and then we use 2D networks to predict structure of interest in the X, Y, X, Z, and Y, Z projections. And then after that we can use this model or probability maps in order to reconstruct the full model. It works really well. I was doing this in MIB, but there is no really single user-friendly workflow for that at the moment. But the alternative way that you can now use this 2.5 depth to color workflow. The idea is that for the training, we extract subvolumes, which could be 3, 5, 7, or 9 slices from the dataset. And then from in each of these subvolumes, we segment only the middle slice. After that, when network is trained, it actually fuses all these individual slices into color channels and apply more or less standard architecture for the training. And then when it's trained, then we can use this to predict our organelles of interest. Here is one of the examples also of the FIB data set of a model of endoplasmic reticulum and mitochondria. And the benefit that 2.5D network can give you, it actually can fill up the gaps which sometimes the 2D network cannot really distinguish. Here's like one of the example of ER profiles, and in 2D model they are not detected, while in 2.5D they are detected. And the added up areas that were added with this 2.5D architecture shown in green here, or you can see the toggling comparison on the left image. It is quite situational. You probably need to have a dataset which is not very heavily anisotropic, and it's also a bit slower. So, for example, this Z to C workflow is about 1.5 times slower than using the similar 2D network. To start, I will download the dataset. The link will be in description, and from this dataset we have actually the trained networks for each of these organelles, but I would like to show the full workflow, and then for that I will only download small dataset, small crop. So I click on this download button, and I will download this to here to my project. And what I will do, I will make my directory for training, and then I unzip this dataset there. So here in this directory, let's delete this zip file, we don't need it anymore. And in this directory we have images, and this is a small crop of this big data set that we deposited, which you can download and play around with it. Now I opened Microscopy image browser, clear everything, and actually as a small example we also have a small test synthetic dataset in the examples. Here is synthetic 2.5D large spots. And what you can do, let's see where we were. You can unzip this to wherever you want. Let's make new project, spots. And then this small synthetic data set should give you the whole idea about how the images needs to be arranged, as well as this data set which is predicted. And in this case it's more like spots, 3D spots, like balls, and also there is a noise, which is like the spots that are present only on a single slice. And the idea of that network, it's trained in order to separate these cases. Let's see the prediction. So as you can see, like for example, this spot is in 3D, so it was detected, while all the spots that are jumping around, they are not detected. So this is the idea of that synthetic data set. It's quite fast to train network for that. But now I would like to concentrate more on this mitochondria example, because it will allow me to show you the full workflow. So let's load this dataset first. This dataset is initially twice downsampled. It is now 5 by 5 by 5 nanometers. But what I'd like to do, I just don't sample it twice more to make it quicker, this particular tutorial. So I go to the dataset, dataset resample, and I just don't sample XY twice. So now my dataset is 10 by 10 by 5. Well, I could downsample Z, but I don't really have that many slices. I'll just keep this 50 slices as they are. And then I just resave it by going to File, Save Image As, and let's name it bin4. And I just delete that one because I don't need it. Alright, so remember, well, I don't need my mirror. Remember that I told you that the idea that we need to segment in a single slice. And how we do that. To do this, I will just load the dataset that I want to segment, and let's say I go to slice number 10, and then I can use any of the tools that we have for segmentation. Now, in this particular case, I'll use segment anything. There is another video that you can find how you can actually install it and how to use it. But mitochondria are a really nice target for this, and I can quickly create the ground truth training set for that. What I do, I just basically click on my mitochondria to select them, and then let's see, just let me to select them and assign to my material. Let's say this one. And then, because I have mitochondria quite easy to do both the training set and the segmentation, and that's basically the reason I picked them. But we also use this 2.5D workflow for segmentation, also other organelles as this Golgi and endoplasmic reticulum. The segmentation of this, or generation of training set for this, is actually also quite nice, because you can still scroll around back and forth to see what kind of data you have, and it allows you better kind of evaluation of structures. So segment anything allows us to do the segmentation with the single click, so I don't have to use mouse just to draw the boundaries. I use a mouse click to define a pixel that belongs to my object, in this case mitochondria. Then I use control click to remove areas that should not belong to mitochondria. And I use shift click if I want to add another area to mitochondria or to existing object. Well, mostly in this particular case, I do it with the click and control click. Now I segmented slice 10. Let's go to slice 25 and repeat the process. I'll just do fast forward here to make it quicker. Now it's done. I segmented 3 slices, slice 40, slice 25 and slice 10 out of this dataset. Now we need to extract this. The easiest way to do that in this particular case is to use the annotation tool here, and then we just click somewhere in the image, so on the slice 25, then on slice 10, and then finally on slice 40. So we have 3 annotations. Then I press the annotation list button to open them up. So this is these 3 points that I placed, and then you can, with right click, you can jump to them. Then we need to select these 3 annotations, right click, and one of the options here is crop out patches around selected annotations. On the website and also in this channel there are more detailed video how it works, how we can use this. Now if we want to do 2D segmentation, then we just need to and we want to crop out the whole slice, then we just need to put in the width and the height just something like a large number to make sure that the whole slice is actually extracted. If we want to crop out 3D objects for 3D segmentation or this 2.5D segmentation, then we press this crop 3D object checkbox and specify what will be the depth of these small subvolumes. For example, if I put 3, then I will crop out 3 subvolumes, and each of them will have 3 sections. If I put 5, then it will be 5. If it will be 7, it will be 7, and so on. Let's take 5. Then we also want to crop out the model, because that we want to use for training, and I check this the crop model checkbox, and I can specify format. And then I also need to specify the output directory. And in this case, let's make a folder, one train, and use it. Also, there is a new option which is called jitter XY centroids. The idea with this, what you can do, you can use get statistics. For example, I can right click on this mitochondrial object, go to get statistics, calculate my objects, break all these things that I segmented, and then I can segment them. Actually, I can see that there is few small problems. Let's just select them and delete. Yeah, so I can see all these objects, and what I can do, I can make new annotations from these objects, and I can use this annotation, this tool, in order to crop those objects. But to make sure that in the central pixel I don't have the object all the time, I can use this jitter in order to shift the boxes a little bit left, right, up and down with this variation in pixels. But now we don't need it because we extract the whole slice or small subvolumes. Right, everything is selected here. The input directory actually, yeah, train select folder. And then I press the crop button, and then there's additional parameters that could be included, and then I think the best is include just the Z coordinates, because in this case we'll know where each particular patch is coming from. And then here in this picture you can see that we have these 3 objects that coming from 25, 10 and 40 slices, and then we extracted also the corresponding models. Let's take a look. For example, if I take this, let's say 25, slice 25, and then I load the corresponding model just by drag and dropping the model and the files into here image view, then you can see that it's 5 section subvolume, and then only the middle slice is segmented. Now we need to arrange this into directories that we will use in our project for training. To do that, there is a description how it could be done. I'll show it again. The tool that can be used for deep learning segmentation is available from the menu tools, deep learning segmentation. Let's move it here. And the starting point you can do by pressing the help button, and the press of this help button brings us to the corresponding panel, description of the corresponding panel. In the directories and preprocessing panel, there are, in the context parts, there are these sections, and when we scroll towards that section, we can see a snapshot with directory tree that explains us how we need to name the directories in order to use this particular workflow. For example, without preprocessing, what we need to do is to place our images and labels that we will use for training into directories that are called train images and train labels. If we have some validation images and labels, then we can place those to validation images and validation labels. And then we also create two other directories, one where we place the images that we will eventually want to predict, and then the last one will be the place where all the results and the resulting models will go. We can also do some pre-processing, and in the case of pre-processing, we can actually, one of these options is to split files to training and validation set. The idea is that all images that we have for training, we put in the images and the labels subfolders under the training part. And then we select the split files for training and validation, and then after that it will split them into these two sets that we will use for training. Again, I will show you this, but this is if you don't remember how to name the folders, this is the very easy way to find out. Alright, so in my particular case, what I do into this one train folder, I just need to create one directory which I called images and one which called labels. And after that, I copy images into images and labels into labels. So this is our starting point. We have a train folder, then we have a folder where we have images that we eventually want to predict. And then we create a new folder where we will put our results. Now let's get back to actual tool, DeepMIB, and let's go a little bit from the top to the bottom. First, we need to select what kind of workflow we use. If we want to use 2D semantic segmentation, then it's 2D, and then within this 2D semantic workflow, we can have access to various network architectures. And depending which network architecture you select, there are certain settings that could be potentially tweaked for that. Then there is a 3D semantic segmentation. In this case, there are just two networks. And then there's also patchwise, which is basically a classification workflow where network predicts what kind of, to which class a patch belongs. There's also another video on the channel about how to use that one. But now let's take a look more on this 2.5D semantic segmentation. In the architecture, there are 4 different options. The 3 of those are called Z2C, which means depth to channels, to color channels. This is what I was explaining in the beginning of the video, when we take slices and then we arrange them as the color channels and use this for training. The first option here, doing slightly different thing. It actually starts with applying 3D convolutional filters. So instead of arranging things into the color channel, it actually does really 3D convolutions on the small subvolumes. I think it's here basically for some tests, because I personally do not really very much satisfied with the performance of this. It's quite slow. And in many applications, it's way easy to use these guys here, and that's what we will use today. These two are, well, let's say how different they are. This UNet allows you to specify how many layers, downsampling layers of the network you will have, and these two use predefined number of these downsampling steps. And one of these is based on this DeepLab version 3 ResNet 18, and then another one ResNet 50 architecture. And this is have more parameters, that has less parameters. So this is more heavier, this is lighter. Well, let's take this one. Then we can select GPU, which we want to use, and then we go to the what would be the network file name. Then I click on these 3 dots, and then I just specify name of the network. Let's say in this particular case we call it mitochondria. Then we can specify that this is DeepLab version 3 ResNet 18 network. Let's put it Z2C, and then let's specify maybe patch size. So we have 5 slices, and XY we can make. This is quite small data set after I don't sample it, so its height is about 390. So maybe we'll do it, let's say 224 pixels, which is basically the standard way how this network was designed. But typically I use way larger numbers. The next step is to specify the locations where we have our data. So I click on these 3 dots, make sure that I have train selected, and the format is AM, which is a mirror mesh format. You can open it with Fiji, but it's the standard format for Amira. Then there's a bunch of formats you can select, and you can also use this bioformats checkbox to press, and then you can have access to use these various microscopy formats. The typical strategy, if you have some standard formats like this, then I do not do any of the pre-processing, which is the other options here, and that was the standard way in the earlier versions of this tutorial. But these days it's way quicker. If it's standard format, just use it directly without pre-processing. If it will be these bioformats, then I would probably do the pre-processing. Then it will probably make life slightly faster. The second, what we need to do is to specify location of images for prediction. Then in this case, it's this to predict folder. And in here we can have our data sets in the images, and then if we have a ground truth, then we can actually create a folder here called labels, and then we can put there the ground truth labels that we can use to evaluate segmentation. Well, I don't have it for this particular one, but maybe I'll copy it later to show how it's supposed to work. And also we need to specify what's the format here. And then in this case, it's also a mirror mesh. So I put a mirror mesh here as an extension. And finally, we need to select a directory for results. I typically name them 1, 2, 3, just in order to arrange them in this logical order. And then called 3 results. The names could be whatever you want. These names are not hard-coded. It could be anything. It's only important that inside the train you have actually images and labels. As well, if we want to use this for evaluation segmentation, then we have images and labels. But you can also don't really have to have this. You can actually place images directly to here. So without these 2 directories. And in this case, it will also work. Let's actually try that. I can delete it because it's probably open somewhere. Okay, well, actually, then in this case, I'll just move this dataset back there. Right. What are the other options? We need to specify what would be the extension of our labels. Now we have .model, which is the model format from Microscopy image browser, but you can use PNG or you can use TIFFs. We can do masking. The idea here is that some areas that we're not sure what it is or we don't want to be used in the training process, we can mask those. And there are 2 ways of doing this. We can either have this as masks. In MIB, I can select an area. For example, take in brush, select a spot. assign it to this mask layer, and then after that I can save this mask. And in this case, those areas will not be used for the training. Or alternative way is to specify all the areas which are 0. In this case, everything else but our mitochondria will be considered as mask and will not be used for the training. In this sense, what we need to have two materials, which one of them would be our object of interest, another will be background, and then I will need to select some kind of areas, let's say all these sort of, and assign them to the background material. So what happens that the blue and purple areas will be used for training, and the areas which are not labeled, which have 0, you can see it's also here, the 0 index will be considered as a mask and will not participate in training. Okay. So we won't use masking for this particular case. Then the next few options here. We can specify fraction of images for validation. For example, if I put 33, remember that I have now 3 images. If I put 33 and select here split files for training and validation and press pre-process, then what happens is that 33% of images will go to this validation set, and then 66% will go to this training set. The training set will be used for training, and the validation set will be used just for validation. Network will not be used these images for training, but only for validation itself. Now we won't use this because we have only few images, and then what I will do, I will put 0 fraction of images for validation, and when I do this, I can copy. In this case, these images and folders will stay, or I can move. In this case, these images will be deleted. Now I use split and copy, and then what I basically did, I just copied the images that were in the images folder in the train images, because that's where we should have images for training, and the same was done for the labels. Now let's go to the next tab, which is the most important tab, which is called training. Here we specify parameters for the training. First important parameter is the input page size. This is an area that network sees at once. Like what you can see here, I already named it my network name, and then I will use these values to initialize, to specify the network input page size. If you don't know what are these numbers, you can hover the cursor over this edit box, and then tells that there should be 4 numbers which specify height, width, depth, and number of color channels in the of our page. The next is the padding. So, if it's same, then the output of the network matches the input. If it's valid, then it's cropped from the sides. Depending what you do, one or the other approach can be used. I think mostly these days we use same, but then when we do prediction, we do it in the tiles that are overlap, and that way we can compensate a little bit for the artifacts that are appearing at the edges of the input pages. Then we need to specify number of classes, including exterior. For example, in this case, if it would be like these would be like real classes, then we have 3 classes: mitochondria, background, and exterior. Because in our case we don't have this background, then we have only 2 classes, mitochondria and exterior, and it should be 2 here. But on the other side, if you use the .model format from MIB, you don't have to worry about this, it will be automatically populated. The same field is actually also available in directories preprocessing. These two are linked together, and it's very important to specify the correct number of classes if you use, for example, TIFF or PNG formats. Then on the right hand side we can have a few additional settings. The first of them is input layer. In this field we can specify additional tweak for images that are going to the network. there are different options. For example, if it's none, then whatever images we have, intensities, they will be moved for the training. If it would be, for example, rescale 0, 1, then we can specify two values, 0 for black and 255 for white, and then the images, the patches that go to network will be scaled from 0 to 1 using these values. And there are a few other parameters of this normalization that you can, it's described in this upper part. Filter size 3, it's not used for this, but if I would go to 2D network, then it will, for example, if I put 5 here and press check network, then this filter size defines what is the filter size which is used at the first step of the network. In this DeepMIB, it's not used as far as I remember. Yes, it's grayed out. So because this DeepMIB is more or less fixed architecture, and the first step they use 7x7 convolutional filters. Okay. Yeah. So this is not used. Then there's activation layer. We can specify there's different activation layers. The standard layers that are mostly used are called ReLU, but you can also have an option to select from few other options. And finally, there is segmentation layer, which is defines, calculates the error of predictions versus what it should be. And yeah, we typically use this custom dice pixel classification layer, which is, but you can also do quite well with the other ones. And on this one, we can also use this exclude the exterior feature, which won't take exterior for calculation of the loss. If you have multi-classes, then it might be useful to take that out, as the exterior is actually the largest material of the model. When this is defined, you can hit check network button, and just to make sure that there are no errors. You can see here I can scroll through the architecture, through the different layers, and I can also see total number of learning of parameters, and then just I should check that there are no errors. The typical errors could come from, for example, from the wrong input page size. Let's say if I put here, then it might complain and saying, no, it was able to do with this. But sometimes it complains, and then in this case, for example, you may need to adjust the input page size. The next section in this dialog is called Augmentation Design. And then in Augmentation Design, we can use various augmentation filters. This is updated dialog, which is a little bit more user-friendly. There is a section for 2D workflows, as this 2D semantic or 2D page-wise. And there is the second section for 2.5D semantic and 3D semantic. Now we're in this 2.5 because we want to try 2.5D. I will show it on this one. It is essentially the same. The only difference is that in 2D, well, I can open them in parallel to show you better. In 2D, this rand Z reflection augmentation isn't available. What it does, it actually makes the first slice the last slice and the last slice the first slice. And this one is not available in this. But everything is exactly the same. What are the options here? There are these, well, let's see, maybe I'll show you on this one first. Yeah. So reset. What it does, it resets these values to their default state as I specified them originally. If you press disable, it actually turned all of these off. If you mess up with any parameters, you can hit reset and it will reset the values in the default state. The first parameter here is the fraction. Fraction defines what's the percentage of patches will be augmented. If it's 1, that all patches that go for training will be augmented. If you put 0.5, then there's 50% chance that these augmentations will be applied, and 50% chance that the page as it is will be used for training. The fill value is the parameter which we use in order to fill the the edges. For example, let's put here -20, -20. Oh, okay, I'm on the wrong workflow. Sorry. Okay, I'll open this 2.4, 2.5D. Let's see. When it rotates, let's put -20, 20. This value, let's put 128, which is gray. If I press on preview, that value defines what will be the color of this. I think these areas are not used in general, but yeah, well, at least the parameters there, we can put any of the numbers. And I think that typically for EM, for electron microscopy, it's better to use white, which is 255, and for light microscopy, 0, which is black. Right, let's each of these augmentations, if you hover over it, you can see that it's described what it does. And there are this number of boxes. The first box defines what is the probability of this augmentation to be triggered. For example, random rotation will be triggered with a probability of 20%. Then if there are these bluish, light blue boxes, then those boxes define the variability of this. In this case, the random rotation, there is a 20% chance that random rotation will be triggered, and there is a number how far it will be rotated will be picked between minus and plus 20 degrees. What I can do, I can hit the I button here at any of these augmentations, and then I can see the effect of this rotation. If I hit it again, then you can see that it shows like another set of these random rotations. And I can look on these values in order to fine-tune a little bit what is the variation of my rotations that I want to have. Each time it shows the random patch, but if I want, and that is defined by this random seed here. When it's 0, a random patch will be used, and you can see that these two images are not different. But let's say if I found a good area as this one, what I can do, I can press this previous seed, and it will populate the seed ID from the previous iteration. And next time when I will show this, preview this, it will always show me the same patch, the same area. And that way I can compare the results variation a little bit easier. Yeah, we can do it for all of these, preview the settings. For example, let's take Gaussian noise, and you can see how variable is this. This is quite noisy, while this one with the minimum number, it's probably as close to the original image as possible. These two, in the intensity and color section, the last two options, hue jitter and the saturation jitter, are for RGB images, and that's why we're not going to use them. Let's see the contrast jitter. You see this is more contrasty, less contrasty. Typically for this, because it's the same data set, we don't really have to do that much these ones, because we are not expecting large variation of brightness and the contrast. But for more generic network, it might be useful to keep these ones as well as these ones turned on. We can also go to the settings, and in the settings we can define how many patches we want to preview. Now it was 3 by 3 and it was 9. If I put 4 here, then I will see only 2 by 2 image. And that way you can actually tweak this to be suitable for your particular application. You can also specify input size in pixels, as well as show parameters for displaying labels that describe what has happened with in each particular steps. Finally, there is the preview button at the bottom. What it does, it will actually show you what actually happens if all of these augmentations that we turned on are actually used. In this case, the first patch, what you see here, it will be reflected around the x-axis and rotated 90 degrees. Then the second patch will be original, nothing will be done with it. But the third one will be actually done like several things will be. It will be X reflection, rotation, and will be something else, which is probably image. Something with image image blur, so it will be blurred a bit. Then the other one also X reflected, Y reflected, and there was something else, and something else. There was 4 operations here. So this way you can actually see the effect of all these turned on augmentations. Right, so we can turn it on and off. So when it's off, augmentations won't be used. But we want to use them. The next section defines how many patches per image we want to have. Basically, I typically want to have one single patch per image and do more iterations. And mini batch size defines how many patches are handled together. And this is, the larger is quicker, but it also utilizes more memory on the GPU. It means if your GPU has limited number of memory, then you may need to decrease this parameter. We can try now with 12. Random seed defines what with a random initializer for the random seed generator. So if you want to get like reproducible results and then compare if you change something, then it's better to keep this parameter fixed. If you put 0, then it will be randomized every time you start the training process. Then the next one important is the training settings. You can access this by pressing the training button. First we can select the solver. Adam is fine. Then we specify number of epochs. One epoch is the in this configuration that one image is seen once by the network. For example, if I put 2 patches here, then it means that one epoch would be like how many images we have multiplied by 2. Okay, let's keep it 1 here. What are the important things? We need to specify initial learning rate. This is quite important. There are some kind of recommendations for different solvers, and for Adam it is 0.001. Then I think the good idea is to actually have this learn rate schedule. It means that upon learning, the network will decrease the variation of this, how it tries to find the learning rates. I'm not sure, depending how many images you have, you can tweak this, the parameter, this how quickly it actually changes this. With that images that we have now, and then because I want to do it quite quickly, I just put it to 10. And the drop rate factor is defined here, which means after 10 epochs, let's say if this was our starting point, then at the epoch 11, it will be decreased by 10%. So it will be 0. Something like 0.9, something like this. And then after 10 more epochs, it will be again 10% lower. So that way, upon training, you decrease the variation of the of certain parameters that network tries to change up to fine-tune itself. There are few other parameters that are more specific for some specific solvers, and then perhaps one of the other important parameters here is the validation frequency. Now I don't have validation set, but if I would have validation set, that would tells me like how frequently the network will evaluate itself, how well it performs. And then now, if it's 0.1, it means that it will evaluate itself after each 10 epochs. Actually, well, just to give you an idea how it works, let's put it 0.5 here, so once in 2 epochs, and the result of our of the training could be either last iteration, so when the network ends, that will be those weights, or the best validation loss, when it actually picks up from this lowest score from this validation process. And I will use this one now, and I will redo this just to show you. I will redo this pre-processing. I will split here. I'll put back 0.33 pre-process, copy. These cannot be removed because of something. Process. Yes. So I have these 3 images here, 1 image is there, just to show how it looks. Then we can also save checkpoints, and then in this case it will create the checkpoint files. Maybe I'll put now 10 just again to show. Export training plots means it will generate comma separated tables with all parameters of the training, and we also can send the reports to the email. There is in the help section you can find how it could be configured. It's quite straightforward, but then you can get notifications on how the process is going with the scores to your email, and it is quite useful, especially if you run this on this kind of virtual machine. Right, when everything is settled, I can hit train, and then it will start the training process. Well, now there is an error, and again, depending on the kind of issues, there could be one or another error. In this case, it actually says that mini batch size 12, it should not be larger than the number of images, because now I have only 2 images, my training set. Then I actually should put 2 here, but then it would be quite inefficient because my page size is quite small. Maybe I'll put, like, let's say 4 pages per image. Let's see, let's try now. Typically we have a little bit more training data, and in this case we can put 1 and then actually increase this mini batch size to be sort of to match those. So what happens now, the training starts. The blue curve shows the accuracy of our training process on the training set, and the red curve shows the accuracy on this validation set. The points here indicate the difference between what network predicts versus what should be there. And our idea is that we want to try to minimize this curve as low as possible. When it's 0, it means that whatever network predicts completely matches whatever is actually fed to it, what it should be there. And actually, typically it's not a good sign. Most likely something went wrong, because it's very hard to expect that network will actually learn that the features so well that it can predict everything. By looking on these 2 curves, as far as they go next to each other, it indicates a good training, but eventually they may start to segregate. And for example, the red curve, which is validation curve, may go up while the training curve will go down. And it means that the network gets overtrained on the training set, and we should stop the training and increase the training set. Now I'll because that was just for the test to show what happens then if I press the stop training any moment, that it will stop the training, and the point that it will pick up in this case would be the lowest point that it will find on this left curve, because in the training options we picked the best validation loss. The best loss in this particular case was at the iteration number 184, which is here. But I mean, it may be quite good already. I don't know. I was thinking that I will do this training only with these 3 images, but use them all rather than use this option. Well, we can try that, and then we can actually compare the results. So now then the network is trained, and then when it's trained, we get these 2 files. The config file has all the parameters that we use for training, and this DeepMIB is the actual network. When it's trained, then we can go to the next, which will be the predict tab, and in this predict tab we can choose the engine. So there is a legacy engine that was used in original versions of MIB, but now all development actually build up around the blocked image engine. Just use that one. The overlapping tiles feature gives us the possibility when we do this tiling, if we use the same padding here during the training, we actually want to use this overlapping tiling. In this case, at the edges of tiles there could be artifacts, and those can be minimized if we use overlapping tiles. So let's put 20 here. Dynamic masking allows to skip areas of white color or black color, whatever we define, but we don't have those in this particular case, so I'll skip this. And we can also include additional padding. It means that at the edge of the image, if there's on the edge of the image could be artifacts, and we can minimize those by extending those if we add padding, let's say 10%, then the sites will be filled with the 10% extra information, which is symmetrical padding. The image would be here, will be symmetrically reflected to this site, and then that image will be used for training. Now we don't need this. Okay, let's put here. And then we just, for the output, we define what kind of format we want to get, either it's MIB format or TIFF, and also whether we want or do not want to have the score files. I'll just keep this both, and then we hit predict. Let's see, prediction started. So it's about, okay, 30 seconds. Now we used, for this training, we used 2 images. We were training for 1.5 minutes, which is not really much. And let's see what kind of result we will get from this. The results, the models that are generated in this operation are go to this results folder, prediction images, results models. It's quite deep, but that's whatever model that we just generated by hitting the predict button. The scores, these are the files that were generated. The scores, which is probability of having mitochondria, and the score network is the file that that was generated upon the training. What it has these comma-separated files with the different parameters of the training, as well as these checkpoint files. Those were created because we had this save checkpoint networks, and the frequency was 10. So every 10 epochs it was creating this file. And then we can continue. If something crashes, then we continue training from any of this. But we typically don't need those if the training was successful. Now we can press the load, let's say load prediction scores. What it will do, it will load the probability. And here you can see in the green the probability of these spots to belong to mitochondria. If we use load images and models button, that it will actually automatically load the model and will load the corresponding, it will load the dataset and the corresponding model. Well, you see here it's a little bit, sort of a bit noisy. The mitochondria are well defined already, but not perfectly. There are this kind of some kind of spots popping up. Longer training might help, but most likely additional images would make life easier. And then we can try that. I'll go back to the directives preprocessing, select here split files for training and validation, and put 0 here, and press preprocess, split and copy. And now what I have only images for training. Now I return back to the train tab, and maybe I'll go to the training settings and update a little bit the learning drop rate period. Maybe to do it a little bit, not going down it as quickly. And I'll change the output network to be the last iteration. Actually, it will be done automatically, but just show you that the final result will be the last point which network will reach. Also, actually, I have one more mistake, or not a mistake, I have a mistake that I made for the previous run, because remember we had 2 images for training and I put 4 patches. So actually what I wanted to put here the mini batch size to be 8. In this way the network will take 4 patches from first image and 4 patches from the second image, put them together and run them at the same time. But I accidentally put 2 there. Now we have, in our training set, we have 3 images. What I can put here, let's say I put 9, and then I put 3. I'll take 3 patches from the first, 3 patches from the second, and 3 patches from the third. Group them together and run through the network, calculate the loss function, and then repeat the process. And these 9 patches would be 1 epoch. We can save network checkpoint files, but I already showed you, and I will uncheck it. And what else? Yeah, and then we can hit the train button. Well, because we already had the training before, now I have an option to continue training from my trained network. In this case, the new training will utilize already learned information, and it will probably be way quicker. If we have some checkpoint files, then actually there will be a list of those checkpoint files here, and we can select from which of checkpoints we want to start. By I deleted those already, but I'll start now new training, just to show you how it will go now with 3 images. Again, we have the training progress window. However, this time we won't see this red curve. We only see the blue curve, which shows the loss function, which is the difference between what network predicts versus what it should be, only for the training set, and there is no validation. What happens in this particular case, the network will get the weights, all these learning parameters that it will kind of it will learn at the end of the network, and use at the end of the training, and use those. Let's wait a bit until it finishes. Actually, a few other notes here. The accuracy in this particular case shows how well network predicts the training set, but it's a little bit not as indicative as this loss function. Also, we have here the preview for the input patches that network gets, and those can be fine-tuned here in the options tab, where we can specify what is the percentage of these patches the network will show. Make it larger, this number will update this preview windows more frequently, but it also will slow down the performance. If you know that everything works fine, then it makes sense to drop this value. Now it's 2%, but you can do it even 10 times or even more lower. Yeah, let's train for like a couple of minutes, and let's see what will be the result. We've been training this network now for 3.5 minutes. You can see that the curve is now plateauing, which means that in general the network learned the main features, and now it just tries to fine-tune a little bit like the edges of mitochondria and the other things. The longer we train would probably still be better, but now we can probably stop it already. Also, there is a few other options, because there was a big drop in the beginning. In order to follow what happens here, it may not be as easy, but what you can do, you can right click over the axis, and then you can specify the Y limit. And if I put now, yeah, I just need to update for that window. For example, instead of 1, I can put 0.2, and then it will actually scale it so that it's easier to see this detailing part of the process, like this. Okay, let's stop training now, even though it still can improve. Now the point, it will be the last point here that was taken with all these learned parameters. We can save this picture by pressing the save plot. This will generate a PNG file which has this picture now. Well, I rescaled it, and that's what it is. It's nice to have for the reference. Then after the finish of the training, we go to the predict tab. We can basically use the same settings as we used before. We can skip the generation of the score files, and then we hit predict. Okay. Now prediction finished, and then we can load images and models. Right, and then yeah, well, this is already better. We had more. We actually trained a bit longer than the other one. Let me bring back the previous window, because the other one was like 1.5 minutes, and this was like 4 minutes and a half. But we have 30% more data, but it also paid off because we have way better segmentation than in the previous time. I can compare this. I can right click over this container. So the container 1 has the our training with the 2 images, and this container number 2 training with 3 images. I can right click and select here link views. And now if I press Ctrl E on my keyboard, I can toggle between the views. And then by scrolling through the dataset, I can visually compare the results. So this is with the 2 images, so we have artifact here, perhaps here, here, there, there. But then in the other one, you see the model is more smooth. There is something here. Yeah, one of these potential artifacts. But in general, the model looks way cleaner. We can evaluate segmentation. For example, if I go and then if I copy the this model that we generated into the labels under the directory where I have images for prediction, then I can use these evaluate segmentation options to compare the results that we generated versus the result that should be. Now the perfect match because I actually copied the same data set. But yeah, well, actually let's do it differently. I will actually delete, let's say I'll delete this area, something like this, and I'll just resave the model. Okay, now if I evaluate segmentation, and there are different metrics that can be evaluated, and I can also save this to a file, like for example Excel file or comma separated value file, then I can have it as the full table. But now I can see that this is the confusion matrix, and then because I deleted some of my mitochondria, now my predictions are just 99.07% correct. But then you can see these potential different metrics for the whole data set and fine-tune the training process to make sure that these numbers are higher. There are a few other things that I probably won't talk now, as this explorer activations or doing transfer learning, and as well as export network, import network. Maybe two other things are that we can load the configs by pressing this load button, but it's also possible just to drag and drop this config into here, into this panel or this panel, and then in this case it will update all the settings from the load all the settings from the config. For example, if I have it like this, what I can do, I can just drag and drop it here, and everything is populated back from the config. Also, let's say we did one training using this network, and now I want to do another training using pretty much the same parameters, for example changing something. In this case, what I do, I go to this options tab, and there is a duplicate, the duplicate button. I can click this, select my target, my source network, and then make the target network. Let's say, for example, I want to do training on another one, for example doing ResNet 50. What I can do, I can change the network name, I can save this, I can load this duplicated config, and then now you can see here I have now 4 files. These are the 2 configs, one of them for ResNet 18, which we used initially, and the other one exactly the same copy of everything, but it just called ResNet 50. And then in this loaded config, the new one, I just changed this to be ResNet 50, and then I hit the training. In this case, my initial training model will stay intact, and all new modifications will go to these 2 new files that I just created. With this, I'm finishing this tutorial, and thank you very much for attention.